Hello, everybody. Welcome to the Oracle RAC New Generation. This is the session in the series of Oracle Maximum Availability Architecture. We're going to go into a deep dive on Oracle RAC, specifically on the new generation. I'm Anil Nair. I'm the product manager for Oracle Real Application Clusters. And some of the ways that you guys can reach out to me is via Twitter or LinkedIn. Also, you want to probably take a look there for some of the session that I've already done. So you might see some information that will be useful to you. So let's get into the safe harbor statement. Obviously, you want to take a second to acknowledge because I might talk about a future product that may not make it into the version. So just want to make sure you acknowledge that. Having said that, let's talk about Oracle RAC. Now, Oracle RAC is the only solution in the market that provides HA and scalability for different types of workloads, which is both writes, reads, and hybrid workloads, all via being active at all the times. What does that mean is that customers can connect to any of the nodes, and if one of the nodes fails, it can actually fail over to the other side. The session can fail over to the other side and continue working, all without any changes to the application. While it is working with all applications, it's also important to remember that this is a benchmark provided by SAP running on Oracle RAC clusters, and you can see pretty much the horizontal scalability achieved, where you go from 2 nodes with 15,000 transactions to about 4 nodes to 30,000 transactions. This is something that is done externally by an independent customer. So this is something that shows the scalability of Oracle Real Application Clusters. Now that we know what Oracle Real Application Clusters is, we need to talk about what is this new generation Oracle Real Application Clusters. Well, new generation Oracle Real Application Clusters is based on 19C, and it essentially allows you to utilize the latest new application development paradigms like JSON, Kafka, blockchain, or whatever, and still put all of these together into a converged database on Oracle RAC and be able to benefit from the scalability and HA benefits, right? This new application would work with Oracle RAC along with the traditional application, which has been working for a long time. So basically, this new generation technology allows all kinds of applications to scale and be highly available with Oracle Real Application Clusters. Now, how does this happen? Well, this happens because there has been a bunch of features that we introduced right from about 20 years since Oracle RAC was introduced. So if you see, these are a very small subset of the features that we have introduced over different releases. And since we talked about 19, Oracle 19 has itself a set of features that help with this scalability and availability. We'll talk about some of the details of these things in the future slides. The new generation Oracle RAC is about 5x times faster when you compare with an application running on a 11G release 1. This is, again, due to some of the features that we're going to talk about in the future slides. Similarly, the new generation Oracle RAC is highly available. So it's about 4x faster when you compare 11G to 12G, and about 1.5 times faster between 12G and 18C. So overall, if I could say, Oracle new generation RAC is about 6 times more available when you compare with 11G to 19C. So summary again, new generation Oracle RAC, the numbers that you saw about 5x times scalability, 6 times more availability is because of architectural improvements. Specifically, we have tuned the algorithms to keep up with the changes in the hardware so that customers can realize the benefits of all these features, scalability and availability, without any changes to their application. And it's available both on-prem, which is on customer sides, and in the Oracle Cloud on engineered systems. So basically, customers can just enable these features by going to 19C and using this the Oracle engineered systems, utilizing the benefits of all of these individual components to come up with and benefit and realize the 6x times improvements and 5x times improvements we talked about. So let's get into some of the focus areas. I've divided this into 2 areas. One is the availability and scalability section, and one is the session management. So let's talk about the availability and scalability section. While RAC runs on individual instances, overall, it is still providing what we call as a simplified buffer cache management. What does that mean is that, if you look at the architecture right now, it's very, very similar to what we call as a single instance architecture. There is nothing that is specifically different, has to be configured. We take care of everything below the covers. Now, if you look at the buffer cache is where we have this unique internal implementation. Again, customer doesn't have to know about it, but this is just depicted here for understanding what are the algorithm changes and improvements. So if you look at the instances as 1, 2, 3, 4, we have some of these things called M. M is a master and B is the blocks or the buffer. So every block in the buffer has a master. And the most important thing to understand is that the buffer and master could be on different nodes. However, the master knows everything about the buffer itself. So if it's a dirty buffer, it's a clone buffer and all that, the master knows everything about it. Now, when we look at so many of these buffers, obviously the more SGA you have, the more blocks you can put in the buffer. The number of masters also increases proportionately. So what we have done is we have optimized some of these things in 19C. What I mean by that is if you look at Oracle RAC processes, specifically the LMS, LMD, LCK, LMON, and the DIAG, we see that we have made it more fine-grained. Making it more fine-grained enables scalability and availability. So if you look at, we have a hang manager running in DIA0, we have the IPC0, which performs basic messaging. They're all as separate processes and separate threads. So if you do a PS minus EF, you would see that now in the 19.4 release, you have something which is running in TS, and in the 12.2, you'd be like, hey, this is real time. Anil, why did we change these LMSs? Well, actually, we didn't change the LMSs. What we have done is we have improved it. So now, in order to find out the actual details of the individual threads of LMS, you need to do this extended statistics or PS minus ELO option. So you could see that the LMS itself is running in real time and some of the threads itself is running in timeshare. Again, why this optimization? Because we found out that there's no point of adding more and more LMSs to be running in real time. What we need is the LMS to run in real time and the CR threads, or what we call LMS CR threads, to run in timeshare. With this optimization, we performed some benchmarks to find out how this whole thing works. So reconfiguration is a step that happens whenever a node joins or leaves the cluster. Obviously, reconfiguration depends on the amount of changes in the buffer cache. Remember, a reconfiguration occurs because if you have 2 or 3 nodes running and one of the node is actually leaving the cluster, the other nodes have to perform and make sure that all the changes in that node which was just evicted has been committed. So if you look at it, basic time with 25 gig, we take 3 seconds, to 100 gig, we take about 8 seconds. So 4x times more buffer cache, but reconfiguration, we have curtailed it to less than 3 times. Similarly, as we get more and more LMSs, so if you look at 32 LMSs, we could get that reconfiguration time down to 3.6 seconds. So basically, with having more LMSs, having more of the CR thread architecture, we are able to reduce the reconfiguration time from 8.3 seconds to 3.6 seconds. This is all possible only because of the changes that we made in the underlying architecture. Now, obviously, when you connect to any of the nodes, you expect, or the session expects, that the result be, first of all, fast and consistent. So if you take this example of a session connecting to node 4, and it wants something that is running on some other node, first of all, it has to find the block master. So it will send a message to the block master. The block master will say, hey, go to node 2, which has some information with an old SCN. And the block itself would be either shipped, or if it needs some, to do a read, it will do the read. Now, regardless of how many nodes you have in the cluster, the max hops is 3. If you see, we only did 3 messages, and within 3 messages, we could get this information. Now, this is, remember, the worst case scenario. It is very possible that the block master and the block itself are on the same node, or if the query could actually be connecting to the node where the block master and the block is co-located, which means your performance will be most optimal when all of the 3 collide, in the sense they are in the or co-locate in the same node. This is important to understand because this kind of steps up correctly into what we call as the optimizations in the Oracle RAC buffer cache management. So in order for optimal performance, we really want to make sure that the resource master is on the instance where the buffer resides. Now, remember, when we start up, how do we know? We don't know, right? Because obviously when we start up, the buffer cache is empty. So we would actually end up having or dispersing the masters across all the instances. We have 2 optimizations which ensure that the master is on the instance where most modification occur. And any, this is during startup. Now, during workload run or runtime, we actually track which block is accessed from which node, and we try to co-locate that master to that block or to that node, which is what we call as DRM, or dynamic resource mastering. We'll get into a lot more details soon. In order to kind of make it at a high level summary, we kind of broke this into 2 separate sections. One is the scalability features and the availability features. So let's look at the scalability features. So we have this LMS CR threads to mitigate performance outliers. What is a performance outlier? If you look at this performance, this is a pretty much very, very good chart of an application, which shows that as the number of sessions are increasing, the transactions per second are increasing, the response times is pretty much under 50 milliseconds most of the time, except there are some outliers here and there. Now, these outliers are a little bit hard to track because the outliers are very few, first of all, and it is for a very short amount of time. And what we found out is these outliers are the result of some specific workload that is deviating from the typical work that is happening on the system. What do I mean by that? So let's explain this a little bit in detail. So what happens is, when you start a RAC instance on a couple of nodes, we assign what we call as couple of LMSs to that. Now, the entire buffer cache is divided by the LMSs, and essentially anytime that an LMS is requested to do work, it'll go and do the work on behalf of whoever requests it. Typically, it is able to do it. Let's say it is having to read, say, 5 to 10 blocks per second. Now, suddenly one query comes in and says, I want you to get me a block which is about 30 or 40 seconds ago. This might require applying a lot of undo, because remember, if you're making changes 10 to 15 times per second, having to read something 30 seconds ago, which require a lot of work. Now, this LMS would get busy trying to do work on behalf of that session, and therefore cause the rest of the traffic to build up, which is what is shown up in the earlier slide, as I said, as an increase or an outlier, right? So what we have done is we have now worked around it by having this feature called CRS Server Threads. So if the amount of undo exceeds a particular threshold, we would go and invoke a thread and say, go do the work for that busy guy. I'm not going to have this build up causing me to have these outliers and affecting the performance of the application. By the way, this is all automatic. We automatically calculate the threshold. We automatically calculate the number of threads. We take into consideration the load on the server. So if it's a very busy server, we will not, go and allocate, additional threads. And remember, these threads are not running in real time. So it's not too much load on the server. So we take care of all those considerations and do what is best to ensure that the performance is not affected. Remember, we talked about how do we make sure that during startup, the buffer master is co-located with the block itself. So what we have done is, during startup, these are separate services on various databases. So if you see the brown service is running on, let's say, node 1 and node 2, then what we know that is, okay, the blue service is unique in the sense that it is only running on node A. So if there is work coming onto blue service, we want to make sure that it's co-located or the block masters are located in node A. we not only make sure that this is done, we actually persist this information into the data dictionary so that during startup, when everything is started up, we actually ensure that, hey, we know that the service blue is accessed frequently from node A, and therefore whatever queries and DML and DDL operations are run, we try to make sure that the master is co-located on this node. This is really optimal because now we have reduced that 2 hops to 1 hop, which is obviously much better for performance. Also, we can use this when we have some kind of plant failover. What I mean by plant failover is, let's say if you have to apply a operating system or firmware level patch on node B and you need to failover certain workload. Now, if this workload has been running for a while, most of your data is in the buffer cache, your queries are being satisfied from the buffer cache without having to rely on physical reads. Now, if you have this feature, what would happen is when we are doing this what we call as a planned downtime, we could actually ensure that the buffer from node B is moved on to the node A, what we call as a feature called pre-warming the instance on node A. This way, instead of your sessions having to rely on going to the physical reads, we are actually being able to provide this information right from the buffer cache. So for many of the sessions, they can't even notice that they are moved from node B to node A. So this is a very interesting feature that kind of reduces the impact of any planned operations. Hang Manager is one of those unique solutions or unique features we have that I can pretty much claim nobody else has. Remember, a Hang Manager not only is detecting a hang, but also providing what we call as hang resolution. This includes application hangs. Now, sometimes developers, application developers inadvertently write code that results in even deadlocks. Now we have a, since 18C, Hang Manager can also resolve deadlocks. We do that by understanding and looking at all the sessions that are waiting for an event. We try to apply the hang detection mechanism, evaluate it. Only if we can confirm, then we do a hang resolution. This is amazing because this all happens below the covers. And we also provide a lot of detailed diagnostics so that, unlike in the past when the session is hanging, the database is fine. The DBA has to work a lot to show the application developer that, hey, your hang is not really a database hang. It is something that is caused by you. Now with this feature, we actually say session blah, this is the SQL, and session blah plus phi, this is the SQL. This is why you're waiting, and this is why it is hung, and you need to fix this SQL. So this is all the information provided to the customer without them having to do anything. This is automatically inbuilt and automatically works below the covers. We also provided a sensitivity setting. So by default, we have a normal setting, but if there's a customer who says, Neil, I really want this to be a bit more quicker, then they can set it up to high. And there, it's an option. So by default, we do normal, and we recommend you keep it at normal. Now let's talk about availability. Now, availability features include some of the things regarding node eviction. Now, if you have played with Oracle RAC, you know that we expect certain nodes to behave in certain way in order to be part of the cluster. If certain node does not behave correctly, which means it doesn't send a heartbeat via the network and the disk, then we kind of have to evict it. In previous releases, we kind of used to go through this mechanism, what we call as the lowest node number. What does that mean? Now, let's say you have what we call as a split brain. So nodes 1 and 2 are on one side, and node 2 and 3 and 4 on the other side. What would happen is we would always keep the node numbers which are having lower node numbers, and we will evict the guys on the right hand side. Now this is the norm, and it used to work for the longest time, I know. With 12C release 2, we introduced this called node weighting. What node weighting does is we actually look at, hey, how much more work is on this side? So if you have a split brain, we have 3 services on this side, 2 services on this side. So obviously there's a split brain. We want to keep the right-hand side nodes available, and we can evict the left-hand side nodes. We also have additional checks. So for example, if even on the right-hand side, let's say we have more services, but if there's a public network failure on both these nodes, then what's the point? Therefore, we would keep the left-hand side nodes in the cluster and we'll evict the right-hand side guys. In case when there is a equal number and then we have public network card failure, we don't know what else we can do. We will fall back to the original scheme, which is to keep the lowest node number in the cluster. Now, obviously, when we do all this automation, some customer would come and say, Anil, no, I actually know what I want to do. So can I mark certain nodes as critical? So yes, you can do that. So this is an optional task. You could do it. This is just for DBAs who want to have absolute control over what happens. In this case, we have marked certain nodes as critical. Then we could keep this node and evict the other nodes. The marking could be at a server side or at the services side. What I mean by that, you could say node number 1 is my most critical and my green service is most critical, in which case you're kind of shot yourself in the foot because you have put something where we don't know which is the right one. So we, in this case, again, go back to our failback mechanism. And we put all this information in the logs and we tell them that, hey, this is what happened. This is the reason why I took out this node. Now, once we evict, obviously we have to reconfigure. Why? Because remember, the node that is getting evicted might have changes or might have some kind of updates which needs to be returned to disk or which needs to be rolled back. Now, this is what this concept of reconfiguration is. Now, with this new feature, we have this called Recovery Buddy. We can do pretty much 6x times faster reconfiguration. Now, how do we do that? Well, remember that on the left-hand side, without a recovery buddy, we have to go through all these different phases. To elect the recovery master, we have to read the redo and apply the recovery. With recovery buddy, we detect and evict, but the rest of the things are done as part of the recovery buddy. So we don't have to do wait for any election of the recovery. We can read the redo. We don't have to actually physically read the redo. We can read it from the memory itself, because the recovery buddy buffer, which can be applied rapidly for recovery and open up the database. So this is one of the reasons by which we have affected the recovery buddy feature to reduce reconfiguration time. New in 21C, which is going to be released soon, is also we are planning to have zero downtime for planned outages. What does that mean is, if you look at these typical 4-node rack, and we have masters and blocks all over the place, in a response to a planned downtime. Let's say we know that certain node needs to be down to apply some operating system patch or whatever, then instead of doing the reconfiguration after, we can do it before. So if you can see by the animation that we automatically move some of the masters beforehand to the other nodes, and the other nodes can therefore make sure that those buffers are updated and therefore don't have to go through this reconfiguration time, which by the way is already low, to even lower, which is essentially zero downtime for planned outages. For multi-tenant, we have improved the scalability optimization. Essentially, what the idea is that one chatty PDB should not affect the performance of another PDB. What this means is, if you look at the left-hand side, if we have, in the SGA a resource hash table, and even though you have 4 PDBs, we kind of hang them off of the same resource hash table. So if I have to go to this green block, I have to traverse each of these resource hash table until I reach this green block. Now, it is possible that the green PDB is not having enough blocks, but still I have to go through the blue PDB and the red PDB and the gray PDB in order to reach my location. On the right-hand side, you see the optimization. On the right-hand side, what we have done is we have divided each PDB into separate domains. So now if I have to go to the blocks of the PDB4, I no longer have to go through the blocks of the green or anything else, because I can map that PDB4 is domain 4. Now I can quickly get to my resource. So this is an amazing optimization which allows us to scale multiple PDBs in the same database, right? Because we don't have to go through what we call as a single domain. We have multiple domains, or a domain per PDB. This also is exposed in another way. So if you have, let's say, multiple RAC instances running different PDBs, obviously you do that via services. Now, if you see this, what happens is if you have messages coming from, say, node 1 to node 2, we would send the messages in an efficient manner. What does that mean is we would not, instead of sending a message from the yellow PDB, we wouldn't even interrupt the red PDBs, because the yellow messages for the yellow PDB messages are for each other. The rest of them do not even have to worry. So we have essentially, by a in-memory optimization, reduced the number of interruptions the red PDB would have when the message is not even for that PDB. Because in this case, as you can see, this is only pertaining to the yellow PDB. So this really improves performance, because it also not only improves performance, by the way, it isolates, so that if the yellow PDB is very chatty, the red PDBs do not have to worry much. Also, remember that if the yellow PDBs decide to, stop, or, if you decide to stop the service on the yellow PDB, the red PDB is not concerned, because there are no changes required for this red PDB that is, made by the yellow PDB. Because remember, PDB level changes are local to the PDB, which is so great, because now there is any reconfiguration changes for anything else, the red PDB can simply ignore it. This is exactly what this isolation, we call it as the PDB service isolation, is. So if there are any events that are occurring on nodes where the PDB is not even up, then we don't even have to be worried about it. So essentially, as you can see in this case, the PDBs are mounted such that the services are gray, brown on the node B, and yellow, this is light green, and red on node A. Now what this means is, if any node is evicted, even planned or unplanned, these guys do not have to be caring, because the changes of these guys are not even on node A. So obviously, we don't have to go through this lengthy reconfiguration process, which is essentially provides us what we call is with PDB service level isolation feature. Okay. Now, when we talk about RAC, how can we not talk about Exadata, which is our premium platform on which we have implemented a lot of optimizations. So Oracle RAC on Exadata, we have amazing optimizations, and some of them I talk about here. One of them is this instant failure detection. Instant failure detection works on both the RDMA-based, InfiniBand-based older systems to the new ROCKY systems, automatically. So essentially, on Exadata, we claim that we can do it, or we can detect a failure of an instance within 0.8 seconds. On generic systems, our miscount is 30 seconds, so we might take up to that time. Now, it's not just our numbers. This is actually taken from the trace file. You can see that we detected a problem with the instance within less than 8 seconds. It's actually 0.733 seconds. And this is something that is only on Exadata or on engineered system. We have a lot more features. For example, we use RDMA to propagate broadcast and commit. If you don't know what broadcast of commit is, essentially, whenever you commit any transaction, we need to broadcast the SCN to the other nodes, and every node has to acknowledge it. On a generic system, this is done via messages. Then in Exadata, in 21C, we'll be using RDMA. If for those who don't know RDMA, DMA is direct memory access and RDMA is remote direct memory access. And because this happens so fast, the benefits are amazing in terms of performance, and not utilizing the CPU of the host system for doing this RDMA transfer is also saves us on CPU time. Continuing on, we also improve the current block reads. We also have this 18C commit cache messaging and the undo block. Again, I'm not going to get into details about it because I already talked about it. If you have any questions, feel free to reach out to me by the mechanisms I mentioned earlier, Twitter or LinkedIn. The right growing index problem is a typical problem in single instance and in RAC. What is the right growing problem is essentially that when you have a sequence that starts from 1 to whatever, as we insert more and more rows, what would happen is, as you can see from the animation, we kind of keep breaking the block into multiple and multiple times. So you can see that in order to get to 11, block number 11, we have to go through these number of blocks, because these blocks are growing on the right hand side too much. This is not really a RAC issue, but you can see that some of this affects scalability. So we have tried to solve this right growing index problem with some of the features, especially on Exadata. Now remember that you could utilize scalable sequences to reduce some of this thing. And we talk about scalable sequences in the next slide. And I also highlighted this as an asterisk here, because this is something that a DBA has to manually do. And I'll explain a little bit more in the scalable sequences section. But right now, let's understand, how do you even find out that, hey, I have a right growing index problem? Well, typically, if you look at an AWR report, you would see the GC buffer release and the GC buffer acquire take about a lot of the time. That's 32 plus 18, 40%, 50% of the time for global buffer contention. And then you can also see that we have 22% of the waits for global NQ handling. Now, these numbers are again not important. What is important is the total amount. You can see that 22% of our time is spent on global NQ handling and about 50% for global buffer contention. So what is the algorithm improvements? So we went back and improved our indexing algorithm so that we can reduce the time we spend on this. So from baseline to optimize, we could see that overall throughput is almost double. We have reduced the split cancels per second from 3.8 to 0.7. Internally, this works so good that between baseline to optimize, we see the 50% better improvement. So you should see these improvements in the RGI workloads if you have any. Sequence contention, as I said, sequences are a bit hard, because especially when you have a sequence that is growing on the right hand side, this introduces some contention, especially on RAC, because now depending on if you have requirements in your business, like, okay, the sequence, you cannot lose a sequence order, you need to make sure that sequences are not cached, then you get into all kinds of performance problems. One of the things, again, you can find out is, by this wait event in the AWR report. So you can see that the NQTX contention is shown as high, and this is because the index is using or based on a primary key, which is based on a sequence, which is why you see this kind of sequence contention. How do you fix it? Well, one of the ways you can do it is using scalable sequences. Now, scalable sequences essentially allow you to define the sequence such that it uses the node number as a key value in calculating the next sequence number. Now, why is it something that you have to do manually? Well, you have to do it manually because, like I said, certain business tables might require that these sequences do not have no holes in them. What I mean is it should be in a continuous 1, 2, 3, 4, 5, 6. There should not be 1, 4, 9. Because when you have scalable sequences and you have more transactions coming from node 4, the node number is considered in that, and therefore you would see this order being a little bit out of order. Again, it's not a bad thing. It depends on your application, but it requires a DBA to come in and look at it and say, hey, this business table might be fine with it, and this may not be fine with it. Obviously, all our sequences by default are not scalable, but you could use that as an option, as a manual task for a database administrator to do so. We have also this in-memory transaction table. In-memory transaction table is essentially a small area of memory to, which contains all the committed transactions. Why is that important? Well, whenever you are running a workload on multiple nodes, remember that certain transactions may not commit, they might roll back, or they might not complete their transaction. We need to make sure that when you have certain primary key indexes and all, that we need to sync up on different nodes. This was done through messaging in the past. Now we actually keep it in the memory of the remote nodes, which makes it so much easier, because now we see a 14 times improvements in these transactions. On Exadata, we also have undo, block, RDMA read, and commit cache. What is it undo, block, RDMA read is? When you are trying to read and undo for a transaction, and if it's on the other side, we have to apply, have the LMS apply the undo, send it as a message. In 19C and higher releases, now we are able to do what we call as an RDMA read of that undo, so it's much, much faster. Same for commit cache. As I talked about earlier, the remote LMS can directly read the commit cache and sends a response time back instead of relying on having to read it via the messaging-based architecture on generic systems. On Exadata, obviously, we know we have this smart fusion block transfer, which avoids or does not require us to wait for an IO confirmation. What is this actually IO confirmation? So if you know about how we do IOs in any system, regardless of Oracle, when you say a write when you call the write API, what happens is we call the API, we got to wait for the IO layer to come and say, yes, I actually wrote. In Exadata, we don't have to do this. Now, why is this? So typically on systems, when we issue a log write, which is the most common thing in a database type of workload, we have to wait for log write completion, because remember, just saying that please write it doesn't mean it's been written. The storage itself could be hung, or there could be other issues at the storage layer. Now, what we do is in Exadata, we are able to do the transferring of the block to the remote side in case the remote side needs it without waiting for the IO completion acknowledgement to come through. This is not possible on generic system, but it's only possible on Exadata for a specific reason, because on the storage side in Exadata, we have the cell software which understands blocks. So the reason actually why we wait for this in a generic system is that if we do this in a generic system and let's say the node, this node crashes, then we have IO from node 1 coming into the storage side without having an IO which was actually written off, but it did not get confirmed. So if you have a recovery at that time, or if you need to recover until this IO, we are kind of lost, right? Because now we don't know how to recover it because this IO was lost. At the storage level, this is only possible and on Exadata is because we understand block structures. So we can actually make sure the order of the writes is ordered, even though it comes from, out of order, because we can look at the block structure and say, okay, we know this SCN should have been after this SCN, and therefore we can make sure the order of the writes is taken care of. You would say, Anil, how much improvement we do? Well, we have seen 40% improvement in throughput, about 33% improvement in OLTP contention with just this feature. So you can see this IO wait completion is a big deal. I talked about RDMA. Now, this is one thing which is really important. If you take the typical performance of a 10 gigi versus Rocky and InfiniBand, we see there's a great improvement. But with this new thing called exafusion, which we have had for a while, this makes it like a 3x time improvement. What does that mean is we no longer now wait for the database to go from the user layer to the sys layer and all that. We bypass these things. So how does that work? So typically, this is how it would work in a generic system. You would see that when we try to write from the global cache, we have to go to the IPC layer, which is an Oracle user layer. Then we do a context switch, because all network transport has to be done via the privileged user or sys user, which will be in the driver stack. Then it will go through the NIC. We will go through the wire. And this has to happen every time. So when you look at your percentage CPU used in your workload, you would see that some certain number is used by sys. With Exadata, what we call as exafusion, we no longer need this to happen. So instead of the buffer going through the OS buffer to the InfiniBand, we now directly go through from the buffer directly to the underlying hardware, and therefore we do not have to do or go through the context switches, which makes it a bit more performant, because there's no more CPU utilized extra for those things. Now that we talked about scalability and availability, we should talk a bit about session, right? Because what's the point of having the databases up and scalable if your application server or if your sessions are unable to benefit from this performance optimizations? So let's look at improved session management. So session management, we have this interesting thing called scan. Not, this is a very unique thing, which what it does is it allows any user to connect to any node, without having to have each of this node information in their connect string. So essentially, they all connect to a scan. The scan listener will redirect work wherever the user wants to. The scan listener also gets notification. So it has payload notification, failover notification that can be updated to the connection pool. So the session can automatically, benefit from any issue if the underlying node is experiencing, let's say, high CPU, or if it's going through a failure condition. So let's look at failure handling. So let's say you have all these sessions coming in and via connection pool. What would happen is if there's a new connection request, it would get routed to one of the scan. It'll say, hey, go to certain node. If it goes to certain node number 1, we'll try to attempt a connection on the VIP. If for some reason while it is taking the connection, or even after it has taken the connection, the instance failed or there's a public network failure, what would happen is the GI or the grid infrastructure will relocate the VIP to the other instance. We'll also issue a gratuitous ARP. There'll be an ARP table update underlying. Again, the client doesn't have to do anything. Once the ARP table is updated, the session that is waiting on this node would get what we call as an instant error instead of waiting for TCP timeout. And it will say, all right, you know what, I have this problem, I'm going to connect to the other guy. And the scan would say, all right, you know what, I don't know what happened to that node. Why don't you go to node number 3, and everything is good. Not only that, it will also send a notification that, hey, I think the node number 1 is bad, so please don't send anybody more to that node. Everybody's happy. That way, we kind of make sure that any failures are communicated right to the connection pool layer, which makes it much more performant efficient for the sessions. The other thing we recommend is a certain TNS connector string. We always say add these things. This is a good values to start from. It assumes that you have a primary scan and a secondary scan, in the sense this is a MAA compliant setup where the primary scan is on site or availability zone 1, and the secondary site is on availability zone 2 or some different location. Always test your failover timings, as I've done here. So I've commented out these timings out, and you could see that my TNS ping took about a minute, which is essentially what is TNS or TCP timeout. But once I made sure that those connections are there, I could almost see there's no timeout wait, so it's almost instantaneous. New in 19C is the way to tag your sessions. So if you have sessions coming in for different kinds of work, for example, if you have some orders, if you have payroll and sales, you could actually tag them by this option called co-location tag, and we will try to send your work to the location where already work is going on for that tag. So in this case, for example, orders is all co-located in node 1 and 2, then we will try to send orders and payroll to the similar sites. For example, here, orders would only go to node 1 and 2, whereas payroll would only go to 2 because it's the only place where the existing work has taken place. We have this feature called application continuity to mask failures. It's essentially not only just to mask failure, we do a failover of the wherever the session is running, and we replay so that the session does not actually see any issue, which is essentially what we call as masking failures. We go through this whole 1 to 6 steps. I talked about it earlier, essentially to let this end user not even know that there's a problem that happened at the front end. Okay. How to enable application continuity. This is a very high level update. You essentially do a servctl command, and you can also use Aura check to see if any of your sessions or your calls are actually protected or not. We're going to have a session dedicated to application continuity in the future where we'll have a lot more details on this. Also in 19C, we have introduced what we call as a transparent application continuity, where you don't need to even go through an application server. You could actually have a direct connection, and the direct connection benefits from all the same features I talked about with app continuity in a similar way. Okay. So in the end, we have this table which gives you kind of like an entry point into what you should use. TAF has been there for a long time. I would not recommend to use TAF. You should look at app continuity or transaction, excuse me, transparent app continuity. And like I said, there will be a session dedicated to this in the future. So all in all, to summarize, with all these features, Oracle RAC is ready for a new generation, the new generation application based on the new technologies, the new paradigms in development. The idea is, instead of having them on different databases synchronized and having all these extra steps to do put them on the same converged database, use Oracle RAC for scalability and benefit from all the availability and scalability options without any changes to your applications, both for new apps and for traditional applications that we have been using for a long time. That's pretty much all I have. And again, just want to highlight that Oracle RAC is not a new kid in the block. We've been using, many customers have been using it. It's a very small subset of customers who are already used it for different types of application. As you can see, there are financials, there are telecoms, there are airlines, there is every kind of different customer base has used Oracle RAC. And this is the #1 choice used by customers already for availability and scalability. Now, having said that, please keep in mind that we'll be having more sessions in this MAA series in the future. We'll announce it in the blogs and Twitter, so please do follow us. Thank you very much for attending this. This is really good of you guys to stay with us for this 45-50-minute session. I hope we covered all the deep features, internal features that we have. If you have questions, feel free to reach to us and we will clarify that again. Thanks.